Hey, this is Charlie Thompson, and welcome to Lab 4. This is the too long didn't read version for temperatures. So in this lab, it's all about temperatures. We're going to talk about temperature scales and how to convert back and forth between Celsius and Fahrenheit. We're going to talk about wind chill, which is the effect of wind making it feel colder. We're going to talk about the heat index, which is the effect of humidity. If it's humid, it feels hotter. We're going to talk about temperature controls, and those are the reasons that some places are hot or cold year-round. And also, part of temperature controls is the reasons that some places have a really big difference between summer and winter, and some places have a very small difference between summer and winter temperatures, and we call that temperature range. Average temperatures, take all the months, add the temperatures together, divide by 12, that's your average temperature. Annual temperature range, you take the hottest temperature and subtract from it the coolest temperature to get the difference between the hottest and coldest temperatures. So there's three big temperature scales. There's Kelvin, developed by Lord Kelvin. Absolute zero is 0 degrees. And this would be a good time to remind you of the difference between temperature and heat, that temperature is a measurement of the kinetic energy of the molecules, and heat is the flow of that energy from one molecule to another molecule. So at zero Kelvin, there is no energy for anything. There is no movement. That is absolute zero. At absolute zero, which is 0 Kelvin, there is no energy for any movement, so nothing moves. The other two main scales are Fahrenheit and Celsius. Everybody in the world, except for pretty much us, uses the Celsius scale. We use Fahrenheit. Hopefully this is review that water freezes at 32 degrees, or rather ice melts at 32 Fahrenheit. Water boils at 212 Fahrenheit. Ice melts at 0 Celsius. Water boils at 100 degrees Celsius. All right. This is, I think, the biggest and most difficult part of the whole lab, and that's the difference between temperatures and degrees. So there are temperatures. Temperatures are a measurement of the kinetic energy. And there are degrees, which are the number of degrees between two temperatures. It's a number of degrees, the degrees between two temperatures. Let me see if I can't explain this. And it's also incredibly complicated. It's totally new. It's very confusing. I don't blame you if at this point you're just going, what the heck is he even talking about? So, degrees Celsius versus Celsius degrees. You already say temperatures correctly, and that's why I say this is the easiest way to remember it. If I asked you how warm it is, you'd say it's, well, you wouldn't say it's 0 degrees. You'd probably say, well, it's like 80 degrees. Because we're in the U.S. and everybody uses Fahrenheit in the U.S., you don't state the system, but if you were going to say a temperature, if you were going to say a temperature correctly, it'd be 0 degrees Celsius. We usually leave off the system when we say the temperature is whatever degrees. So if you're saying it's whatever degrees, that's a temperature. If the last thing is degrees, then what you're talking about is a number of degrees or degrees. So 100 Celsius degrees, those are degrees. There are 100 Celsius degrees between 0 degrees Celsius and 100 degrees Celsius. Those are two temperatures. But there are 100 Celsius degrees between 0 degrees Celsius and 100 degrees Celsius. That would be 100 Celsius degrees between 0 degrees and 100 degrees. And the important thing is you need to use different formulas depending on if you're calculating a temperature or if you're calculating degrees. So, 32 Fahrenheit degrees, is that a temperature or degrees? It's a number of degrees. 32 Fahrenheit degrees, so that's a number of degrees. 32 degrees Fahrenheit, if you leave off the system, you just say, it's 32 degrees. That's a temperature. The difference is where the Fahrenheit and degree symbol are, degree symbol and Fahrenheit. If it's Fahrenheit, then degrees. If the last thing is the degrees, you're looking at degrees. If the last thing is the system and the degrees are in the middle, so that you could just say 32 degrees and leave off the system, you're talking about a temperature. Degree conversions are super easy. So 100 Fahrenheit degrees equals 100 Celsius degrees. So since the last word in there is degree, you know that we're talking about degrees. 18 Fahrenheit degrees equal 10 Celsius degrees. 100 Celsius degrees are the number of degrees between 0 Celsius, freezing, or rather the melting point of ice, and 100 degrees Celsius, which is the boiling point of water. There are 180 Fahrenheit degrees between the melting point of ice at 32 degrees Fahrenheit and the boiling point of water, 212 degrees Fahrenheit. So there are 180 Fahrenheit degrees between 32 degrees and 212 degrees. So if we divide both sides by 10, you get 18 Fahrenheit degrees equals 10 Celsius degrees. Divide that by 10, 1.8 Fahrenheit degrees equals 1 Celsius degree. So there's the degree conversion. 1 Celsius degree equals 1.8 Fahrenheit degrees. You just multiply or divide by 1.8, depending on which way you're going. Celsius degrees times 1.8 equals Fahrenheit degrees, right? 100 Celsius degrees times 1.8 is 180 Fahrenheit degrees. Fahrenheit divided by 1.8 equals Celsius degrees. Again, these are the degree formulas. These are not the temperature formulas. So 180 Fahrenheit degrees, divide that by 1.8, you get 100 Celsius degrees. So like I said, degree conversions, you're either multiplying or dividing by 1.8. Temperature conversions have a 32 degree offset for the Fahrenheit system. So we know that water boils at 212 degrees Fahrenheit. That is a temperature. 212 degrees Fahrenheit equals 100 degrees Celsius. Those are both temperatures. 32 degrees Fahrenheit equals 0 degrees Celsius. Those are another set of temperatures. So we know 1.8 Fahrenheit degrees equal 1 Celsius degree. And so we're going to use that to develop this formula going from Celsius to Fahrenheit. And one of the things I like to do is to check myself with numbers that I already know are equivalent. So let's make sure we've got the formula right. So degrees Celsius, 100. 100 times 1.8 is 180, plus 32 is 212 degrees Fahrenheit. So 100 degrees Celsius is a temperature. 100 times 1.8 is 180. 180 degrees plus 32 is 212 degrees Fahrenheit. And then let's see if it works the other way. Fahrenheit minus 32 divided by 1.8 equals degrees Celsius. So that's, again, that's a temperature. Degrees Celsius is a temperature. So if we take 212 degrees Fahrenheit, subtract 32, we get 180 degrees Fahrenheit. Divide 180 by 1.8, and you get 100 degrees Celsius. So that's the temperature conversion formulas. If the numbers look like this, you use these formulas. Rounding. Oh, I'm so glad I remembered to put this in. The answer has to have as many decimal places as the question. The output has to have as many decimal places as the input. This is incredibly important for this lab. I mean, if you're a real scientist doing real sciencey things, you would be doing this because it's incredibly important. For this class, it's also incredibly important, especially for this lab. So we know that 50 degrees Fahrenheit equals 10 degrees Celsius. Those are temperatures. 50.5 equals 10.3. So this is rounded to one decimal place. This is rounded to a whole number or an integer. This is rounded to one decimal place. So if I asked you to convert 50.5 degrees Fahrenheit into Celsius, the correct answer would be 10.3 degrees Celsius. If the question said, hey, take 50.55 degrees Fahrenheit and convert it to Celsius, the correct answer would be 10.31. 2 digits, 2 digits. Input, 2 digits. Output, 2 digits. Wind chill. That's the effect of cold and wind to make it feel colder. I go over this in the longer video. You take the input of temperatures. Here we have temperatures in Celsius. And often the diagram itself will give you information to help read it. So we've got the temperatures in Celsius. If they're in parentheses, they're temperatures in Fahrenheit. So 4 degrees Celsius, 40 degrees Fahrenheit. -1 Celsius, 30 Fahrenheit. And then we have wind speed in kilometers per hour. And if it's in parentheses, it's in miles per hour. So you just find the wind speed 32 kilometers an hour, and the temperature, if it's -1, and a 32 kilometer wind speed makes it feel like -8 to exposed skin. That's it. You just find the wind speed and the temperature that I'm asking about, and there's your answer in degrees Celsius and degrees Fahrenheit. Or rather, Celsius degrees and Fahrenheit degrees, because those are temperatures. And then the colors just tell you how long on exposed skin to frostbite. The purple, it's 5 minutes. The blue, it's 10 minutes. The light blue, it's 30 minutes. And I guess under these temperatures, you're not going to get frostbite. So it looks like frostbite probably starts around -30 or so. That's the wind chill table. Next up is the heat index. You may have heard it's a dry heat. The more humidity there is, the less our bodies can cool ourselves. This is the National Weather Service Heat Index chart. Across this side, we have relative humidity. Across this side, we have temperature in degrees Fahrenheit. So if it's really dry, for example, I remember I went to Arizona once and I was helping my uncle and cousins. We were working on cars outside. Let's just pretend it was 100 degrees with 5% relative humidity. So we have 5% relative humidity, 100 degrees. The real field temperature was only 93. It's so dry that your sweat is evaporating before you notice it. That's called insensible perspiration. That's what helps keep us cool. And on the other hand, if it was 94 degrees, I'll just make it 90. 90 is good. If it was 90 degrees with 90% relative humidity, the real field temperature would be 113 degrees. And then extreme danger, danger, extreme caution, caution, likelihood of heat disorders. So the hotter and humider it is, the less humans enjoy it. Principal temperature controls are the reasons that places are hot or cold year-round, and also the reasons that places have high annual temperature ranges or low temperature ranges. So some places are just hot all year, some places are cold all year, some places are hot in the summer and really cold in the winter, and other places it's just like warm all year round. So let's find out why. It's cool to be high. By this, I am, of course, referring to latitude and elevation. High latitude at the poles, it's cold. High elevation in the Rockies, in the Sierras, it's cool. So the main temperature controls, these are the reasons that it's hot or cold, or there's a high or low temperature range. The main control on average temperature, I'm going to give you a second to think about it. It's latitude. To determine average temperature, you just add the temperature of each month, divide that by 12. For temperature range, that's the difference between summer and winter. You take the summer high, subtract the winter low, that gives you the temperature range. Temperature range is also largely a function of latitude. So latitude is a key player in both average temperature and temperature range. So latitude, land-water heating differences. The ocean doesn't change temperature. The land heats up and cools off really quickly. Ocean currents, we'll look at a map. That'll make more sense. Ocean currents and sea surface temperature. If the ocean's warm offshore, where you live will probably be warmer and rainier than if you have a cold ocean current. All of the east coasts, all over the world, all the east coasts have warm currents, so they're more humid. They get more rain in the summer. All of the west coasts have cold currents, so they get less rain, it's less humid. Elevation, high elevation makes it cold. So latitude determines average temperature. The tropics are hot, the poles are cold. High latitudes are cool, low latitudes are hot. High latitudes at the poles, low latitudes by the equator. Temperature range. High latitudes have high temperature ranges. Low latitudes have low temperature ranges. So if you wanted to live in a country where you wore, well, I don't know, shorts and maybe a sweatshirt, maybe sometimes, you'd want to move to the tropics. So let's look at principal temperature controls. Let's look at latitude and its effect on average temperature and temperature range. So the two things, yeah, I love this chart. We've got Brazil, Salvador, Brazil, 13 degrees south, New Orleans, 30 degrees north. So we're going from almost by the equator to higher latitude, Montreal at 45 degrees north, and then finally Barrow, Alaska at 71 degrees north. If they're at 71 degrees, that means that they're above the Arctic Circle, which means that they're going to have several months with absolutely no sunlight. So you'd expect to see a really big range of temperature if they're going from 24 hours of daylight to 24 hours of darkness. On the other hand, at the equator, every day is 12 hours long pretty much. So you can see the difference. This is 70 degrees, that's 80 degrees. They've got like a 5-degree temperature range around the year, and it's also warm. Looks like the average is probably 77 degrees, someplace in there, as opposed to New Orleans. So now we're going from 10 to, I don't know, 30, so like a 20 degree Celsius degree range, about 20 degrees in there. And the average temperature you can see is cooler. It's like upper 60s. As we move closer to the North Pole, we go to Montreal. Now the average temperature is looking right around freezing, and the difference from summer to winter is, let's see, if we say negative 10 to negative 22. So it's like a 32 degree Celsius range, and an average temperature of around 45. And then finally Barrow, Alaska. Remember, they're getting several months of complete darkness, some months of 24 hours of sunlight. So their temperature range is going from negative 30 up to 4. So look, we'll just call it 33 degrees. So like a 30 degree temperature range and an average temperature of, I don't know, negative 15 or so Celsius. So the closer to the poles you are, the colder it is. The average temperature is colder, and the temperature range is higher. The closer to the equator, the warmer the average temperature is, and the smaller the average, or smaller the range is. The temperature range, and this is why they say night is the winter of the tropics, because the difference between, 3 o'clock in the afternoon and dawn, that difference is much, much bigger than the difference from summer to winter. They really don't have seasons right on the equator. So latitude is going to be the main driver for average temperature and also for temperature range. Land water heating differences. Water doesn't change temperature easily. Water heats and cools very slowly. If you're by the coast, you're going to have a small temperature range. If you're well inland, you're going to have a large temperature range. We refer to this as continentality. If you're way inland, far away from the coast, you're in a continental location. If you're by the coast, you have a more a marine climate. Yeah, water when it gets hot evaporates, absorbing heat, cooling the water left behind. So it's very hard to heat water. As you heat water, as you add heat to it, the water evaporates, and in the evaporated water is that heat that you use to warm it. Also, water moves around. Water is transparent. So instead of just shining on the surface, water warms up a larger volume. Yeah, it's pretty good. Oh, water also has the highest specific heat. It takes way more energy to heat up water than it does the land. So here we've got two locations. We've got San Francisco and Wichita, Kansas. This is important, especially for my football players that are hoping to transfer someplace. This is what you're looking for, or what you're going to get yourself into if you move to the middle of the country. Here we have San Francisco, ranging from the temperature range from 50 to, 64. So the average annual temperature is about 60 degrees. Wichita, Kansas, well inland, they have a temperature range going from 30 to 80. So they have a 50-degree temperature range over the course of a year, as opposed to a 13-degree range over the course of the year. The average temperatures are pretty close, 14.6, 13.7. Wichita's slightly cooler, but you can see their summers are hotter and their winters are cooler because they're inland. So they're cut off from the moderating influence of the ocean. Ocean currents and sea surface temperatures, I mentioned this. Warm currents are off of all the east coasts, cold currents off the west coasts. Warm currents evaporate, like the Gulf Stream and the Gulf of Mexico, creating extremely humid conditions in the American South because the water is warm and therefore it evaporates easily. Extra moisture for summer rain. If you live on the East Coast, you get summer thunderstorms because you've got that super warm water offshore. On the West Coast, we rarely get thunderstorms because we have a cold current offshore. So here you can see the patterns of cooler water coming up, coming down. This is the Japan current coming down, becoming the California current. It's a cold current. On the other hand, well, the oceans in the northern hemisphere rotate clockwise. So the water moves along the equator, getting warmer and warmer and warmer, goes up the east coast, dumps its heat to the Arctic, and then you get a cold current coming down the west coast. Warm current coming up the east coast, cold current down the west coast. Warm current up the east coast, cold current up the west coast. If you're on the west coast, there's a cold current. If you're on the east coast, there's a cold current. Elevation. High elevations are cool. Is that it? High elevations are cool. Average temperature. So looking at average temperature, you can see, for example, across the plain states where everything's flat, it's predominantly latitude, hot to cold, combined with elevation. So some places like the Tibetan Plateau, you can see it's much, much colder there than at the same latitudes. You can see the Andes Mountains, you can see the Rockies, you can see the Appalachians, you can see the Sierras, the effect in having colder temperatures. The interior of Greenland, it's getting colder and colder because it's higher and higher and higher. So average temperature is a function of latitude and elevation. Temperature range is the difference between the summer high and the winter low. It is going to be latitude and continentality. So you can see there's like this concentric ring pattern across North America. There's latitude as you go farther north, the temperature range on the equator, 0.5 to 13 degrees over the course of a year. As you move away from the equator, the temperature range gets higher and higher and higher, higher and higher and higher. And as you move inland at the same latitude, the temperature range gets higher and higher and higher. The highest temperature range in the world is in Siberia because of high latitude. And also they are in the middle of the continent. The prevailing winds in the mid-latitudes are out of the west. So the prevailing winds are blowing from west to east across Eurasia. So by the time wind and storms make it to here, they've had to go across all of the largest continent. So extreme continentality. I know there's water right there, but the wind is coming out of the west. You can see the extreme difference in temperature range that continentality causes at high latitudes. With a big landmass, you can develop extreme temperature ranges. In the southern hemisphere, the temperature ranges are all lower because there's no landmass. Well, there's Antarctica, but nobody lives there. So there's no big landmass like Eurasia and North America going across, for example, the Arctic Circle or the Antarctic Circle. There's Antarctica, but there's no big landmass in the mid-latitudes. So South America, a little bit of, well, New Zealand's an island, so they have a low temperature range. Every place is fairly close to the coast and at a lower latitude. Higher latitude, you expect to see higher temperature range, but there's no land in the southern hemisphere. So there's this really interesting mismatch in temperature range and land masses in the northern and southern hemisphere. So temperature range is a function of latitude. The higher you go in latitude, the higher the temperature range is. For example, across Greenland now, just looking at temperature range, as you move north, the temperature range gets bigger. And as you move inland, the temperature range gets bigger. Like you could do a transect moving at 40 degrees from the coast to inland, back to the coast, the range is going to start low, get high, and go back low. Same thing across Africa. Same thing across Africa, to a much smaller degree across South America, to a much smaller degree across Australia. So temperature range, latitude, continentality. So here we've got a map of average temperature again, showing low average temperature at high elevation or high latitude, and high temperature at low latitude. Average temperature across the U.S., you can see the effect of the Appalachians. They're higher in elevation, so you have colder temperatures. Also the Colorado Rockies. The Colorado Rockies. The rest of the Rocky Mountains, they're higher in elevation, so it's colder. The Mexican Cordillera, the mountain range in the interior of Mexico, it's high, so it's cold. Here you can see the transverse range. You can see the Sierras. You can see the Klamaths over here. You can see the Cascades up here. Slightly colder temperatures because the elevation is higher. Colder temperatures because the elevation is higher. Colder temperatures because the elevation is higher. Colder temperatures because of latitude. In fact, across Texas to Oklahoma, you can see the temperatures just keep dropping. The average keep dropping and dropping and dropping and dropping and dropping, because here there's not a big change in elevation. It's just latitude. Here there's a change in elevation. 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 And it occurred to me, a lot of you probably aren't super familiar with the physical geography of the United States or of the world. So I've included, where did it go? A couple maps showing which areas are higher in elevation. Appalachians, the Rockies, the Sierras are higher in elevation. So temperature range, it's the same thing. It's latitude and continentality. You can see high latitude, inland location, very high. On the coast, in the tropics, very low temperature range. The same sort of concentric pattern across Australia, same kind of concentric pattern with the coast having a lower range, and high latitude interior location having the highest temperature range. Close-up of temperature range across the U.S. As I mentioned, water. So here we've got the Great Lakes. They're not changing temperature a whole lot over the course of a year compared with the land around them. So we've got latitude for annual range, and then continentality for annual range. Elevation, again, higher elevations are going to have cooler temperatures. Here you can see the Cascades. Here's the Sierras. Here are the Rockies. Here are the Appalachians, showing the comparison between average temperatures and elevation. So high elevation, high elevation, high elevation. You'd expect to find cooler temperatures. And a different map, the Sierras, the Rockies, the Appalachians, the Mexican Cordillera are the high elevation regions that I would expect to be cold. Rounding, I talked about this before, but I just want to emphasize it one more time so that you get the questions right and understand why you're getting them right or wrong. The answer has to have the same number of decimal places as the question. So if you're given convert 20 degrees Celsius, the answer would be 68 degrees Fahrenheit. Integer, integer. If you're given 20.2 and you do the conversion using the formula, you're going to get 68.36. But you need to round that to one decimal because the question, 20.2, had one decimal place. So the correct answer would be 68.4. If you tell me 68.36, that is wrong because it doesn't have the right number of decimal places. So for this lab, if I ask you to convert 20.2 degrees Celsius and you tell me 68.36, I'm going to take off points. If you tell me 68.4, that'll be perfect. Same deal. If you're given 28.22 degrees Fahrenheit, and again, that would be a temperature, right? 22 degrees is a temperature. If you plug that into the temperature conversion formula, the answer you come up with is 68.396. That's wrong. Well, I mean, it's correct, but it's not the answer that I want. If I gave you 20.22 degrees, the answer's got to be 68.40. If the final digit is a 0, normally you would round. However, for this lab, if the input has 2 digits, the output has to have 2 digits. 68.396 is wrong. 68.4 is wrong. 68.40 is correct. So if the input has 2 digits, the output has to have 2 digits, even if the last digit is a 0. And I know that you're used to rounding because you'd look at that and go, that's not telling me anything. There's nothing there, so I'm just going to eliminate it. But that extra decimal place was there with the input. It has to be there with the output. Otherwise, you're losing information. Like whoever captured this temperature reading of 20.22 degrees, this 100th of a degree was important. This indicates that this tells you that whatever we're measuring it to 100th of a degree. We're collecting the data, we're analyzing the data, we're measuring the data, and it's precise to 100th of a degree. This is precise to 1/10 of a degree. That's precise to 1,000th of a degree. If the input is to 100th of a degree, the output has to be to 100th of a degree. That's it for the too long, didn't read intro to Lab 4 on temperatures. I hope you do great. If you have any questions, please come to Zoom. If you can't make the Zoom times, hit me up. Tell me what times are convenient for you. We'll figure out something. I am happy. Doesn't matter what day it is. Doesn't matter if it's a weekend. I'm happy to set up a Zoom session to go over anything that you'd like to talk about.